In the event that you're keen on something so far out in the universe that you won't ever see it, how would you go about it? A telescope is sent off into space. The organization NASA has done this by sending the James Webb Space Telescope into space. One of the spots the space telescope will look is the actual edge of the universe. The discoveries at the horizon of the universe are probably going to be unnerving. Assuming we construct the primary telescope, what will we see when we watch out at the actual edge of the universe? What are the best repercussions for you? In this episode, we'll dive into the stunning revelation made by the James Webb Space Telescope near the edge of the universe and perceive what it means for everything. Starting from the earliest days of recorded history, people have been interested about the ground underneath them, and as exploration technology has further developed, that interest has extended to embrace space. Albeit the thought behind telescopes has been around since the late 16th century, the main telescopes weren't made until 1608 in the Netherlands, and their discovery was essential to our advancement in cosmology. As the tale of Galileo and his adjustable perceptions shows, a strong commitment to review and gathering data can definitely modify one's viewpoint of the universe. A couple of space experts at the time, including Galileo Galilei, pointed their telescopes upward. Most early telescopes were utilized for earthly perceptions and assisting tasks like studying and military strategies. Subsequent to finding out about the Danish point-of-view glass in 1609, Galileo was motivated to fabricate his own telescope. His progress in displaying the instrument procured him a lectureship at the college that would last the remainder of his life. Galileo invested a ton of energy perfecting his telescope. The first he made could amplify objects by an element of 3, making them look multiple times bigger than they were. Later renditions of his telescope could amplify by a variable of 8 and, in the end, by a component of 30. Telescopes and space are indivisible. This is because space is so huge. Proxima Centauri, the closest star to Earth, is situated a good ways off of around 4.2 light-years. 1 light-year is around 5.88 trillion miles. Or 9.6 trillion kilometers. That's an extraordinary 25 trillion kilometers between Earth and Proxima Centauri. In spite of the fact that Elon Musk's colonization exertion on Mars is very close to Earth, volunteers should venture out for quite a long time to arrive at the red planet and set up a long-lasting home. Telescopes are utilized when the distance is incredible enough. The unimaginable capacity of amplification has permitted us to investigate these wonderful bodies more meticulously. These telescopes see into space from their roosts on bodies in orbit, for example, the Sun or Earth. Hubble is one such telescope, and it has been returning stunning photographs of the universe for a long time. However, a more fit and complex eye has been embedded in space, and it will assist us with finding out about the universe's edges. The James Webb Space Telescope, JWST, is displayed here. Despite the fact that Galileo probably wouldn't endorse a telescope factory utilizing individuals from everywhere the world and burning through great many dollars every year on innovative work, defenders insist the investment is beneficial. The James Webb Space Telescope, JWST, will be the main observatory for a long time to come, and great many stargazers from one side of the planet to the other will use it during the following 10 years. From the initial blaze of light following the Big Bang, through the formation of nearby planetary systems that might support life on planets like Earth, to the development of our own nearby planet group, each stage throughout the history of our universe will be investigated. The detectors in the telescope's cameras and spectrometers are sufficiently delicate to record incredibly weak signs. The near-infrared spectrograph, NIR spec, is a solitary gadget that can see up to 100 objects simultaneously due to its microshutters, which might be set to various designs. Webb also includes a cryocooler, which is used to bring the temperature of the mid-infrared detectors in another instrument down to a successful 7 Kelvin. Precisely how would we decide the presence of anything outside our observable universe? For example, we might derive that the universe is spatially flat on the largest scales and is neither positively nor negatively curved to an accuracy of 0.25%. Based on our observations and the known key rules that govern our observable universe. Assuming the laws of physics as we know them hold, we can set a limit for the size of the universe before it starts to fold in on itself. The best data for our extrapolation comes from the Sloan Digital Sky Survey and the Planck satellite. If the universe does ultimately fold in on itself, The observable part we see should be no less than 23 times bigger than the detectable region's range, as suggested by the two sources. This implies that the invisible universe has a width of no less than 23 trillion light-years and a volume of space that is in excess of 15 million times greater than the volume we can observe. Assuming no topological irregularities, that said, there are considerations that propose the invisible universe should be far bigger. Can you name the farthest object overhead that the human eye can distinguish? For one, there are galactic features that we probably might never have an opportunity to see in the course of our lives. Why? The current area of the cosmic event horizon is around 16 billion light-years from Earth. It is the finished line in sight, to put it bluntly, not at any point in the near future. If light somehow managed to start heading our way now from this distance, it would take this long to arrive. Thus, the expansion of spacetime is quicker than the speed of light. Beyond 16 billion light-years, the universe is growing faster than light can travel, with as little luggage as possible, and will never touch us for the very reason nothing that happens today outside the vast event horizon will ever be visible to us. However, modern telescopes like the James Webb Space Telescope, JWST, allow us to peer much further. The GNZ11 galaxy, situated around 32 billion light-years from Earth, is the farthest known galaxy. Please note that this is still under determination after considering the accelerating expansion of the universe. The so-called surface of last scattering happens about 46 billion light-years from Earth. This is what you will see regardless of what direction you turn your head. The surface of conclusive scattering, after recombination and photon decoupling, looks like a homogeneous circle of haze from which the first photons of the cosmic microwave background radiation exuded. It is the source of the earliest light scattering, yet the remainder of what we can see, which is unexpected given its name, is the finish of the observable universe, or the farthest point in reality that people are capable of noticing. Everything beyond this is considered a part of the dark universe. For now, this is the horizon of our visual insights, yet not of our creative limits. Continue now past the known universe. I don't have the foggiest idea what could reside here. Just the previous circumstances at a single point in space have been examined. May conceivably exist there. There is a much more unfathomable secret. The particle horizon is the farthest point into the past that should be visible, and it agrees with the edge of the perceptible universe. This suggests the question: is this universe boundless? Since our perceptions have all been made with Earth as the point of convergence and with the assumption that time goes in reverse with increasing distance, considering that Einstein's theory of relativity expresses that a boundlessly flat universe should exist, we can safely assume that it is. Yet again, the universe has no limit or cutoff. Anyway, it is as yet hazy whether the universe is limitless. While the hot, enormous detonation might mark the start of the perceptible universe, it doesn't check the start of existence because before the big explosion, the universe encountered a time of grandiose expansion, during which it was loaded up with energy characteristic for space itself, growing at a consistent, remarkable rate and creating new space so quickly that the littlest actual length would be extended to the size of the currently recognizable universe every 10 raised to the power of 32 seconds. While local expansion has halted, there are still three major issues that have a bearing on the complete volume of our universe. These issues revolve around whether the universe has a maximum cutoff. First, how tremendous was the piece of the universe that saw post-inflationary development and yielded our hot big explosion? Second, is it true that the universe will continue to expand forever, as per the theory of continuous expansion? The span of expansion preceding its end, which led to the hot big explosion, is the third question. Proof for an edge to where expansion occurred may show up in a year, and we might need to straighten out our perspective on the universe. It's also possible that several parallel universes exist, each with its own set of physical, inestimable designs and its own set of physical laws and physics. With this, the possibility of complicated life on one of the innumerable universes known to man becomes even more intriguing. There should be a dramatically huge number of air pockets, each of limited size and scale, detained within the enormous swelling spacetime. In such a case, what does the horizon of the universe look like? Despite the fact that you might have heard of flat earthers and thought they were insane, it's possible they could be right if they extended their flat surface plan to the whole universe, not just the Earth. If you're struggling with envisioning the universe as a flat scene, cheer up. As per Einstein's theory of general relativity, the speed of light is unaffected by the distorting of spacetime caused by gigantic objects like stars and black holes. It's the most common explanation, given that the whole discernible universe is held inside an event horizon, a limit beyond which no light can travel and is growing at a rate much greater than the speed of light, much the same way to a black hole's event horizon. But in reverse, the particle horizon defines the edge of the universe. It's important to note, however, that the universe doesn't end where you might expect it to. How should you envision that, assuming you reach the edge of the universe, you'd be able to turn around and see a zoomed-out perspective of everything, including each galaxy, planet, star, and so on? Anyway, this is probably not the most ideal way to think about it, at least not as far as space, as there would still be more universe, even if you found the edge. The concept sets that it is absolutely impossible to get around this problem by considering the universe a thing or a vantage point, picture being beyond existence, ready to grasp the whole universe in your hand, because the universe is independent. Humans will never truly become aware of a past. At least, not without interstellar travel. This means that the universe is probably spherical and maintains its size in your grasp as its parts move around. Humans continue to explore the universe, but we remain limited by the constraints of both reality. While the James Webb Space Telescope, JWST, can capture pictures and data from parts of the universe that are far beyond our reach, it also faces inherent limits in our ability to truly understand all that lies beyond our detectable universe. The JWST is a staggering accomplishment, capable of looking deep into the past, observing galaxies as they appeared billions of years ago, and offering a brief look at the universe's earliest moments. Anyway, even with all its cutting-edge technology, there are parts of the universe that will remain forever beyond our control. The immense distances, the expansion of the universe, and the speed of light create barriers that even the most refined instruments can't overcome. One of the principal challenges in investigating the universe is the concept of the universe's expansion. Since the Big Explosion, space itself has been expanding, causing galaxies to escape from us at a steadily accelerating pace. This expansion isn't just happening back and forth, but is also speeding up, meaning that regions of the universe are moving away from each other faster than the speed of light. This is a key reason why the discernible universe has a breaking point. Beyond a certain distance, objects are retreating from us faster than light can travel toward us, making it impossible for us to observe them, even if a spacecraft were to travel at nearly the speed of light. It would still never reach these distant objects because the space between us and them is expanding too quickly. In addition to the expansion of space, there are other factors that make our understanding of the universe so challenging. One of these is the concept of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Despite being responsible for the majority of the universe's expansion, dark energy remains largely unknown to scientists. While we can observe its effects, we don't yet have a clear understanding of its properties or its ultimate role in the universe's evolution. This is just one of the many mysteries that continue to fuel scientific interest and investigation. Moreover, the existence of dark matter adds another layer of complexity. Though we can't directly observe dark matter, its gravitational effects on visible matter provide indirect evidence of its presence. Dark matter is believed to make up around 27% of the universe's mass-energy content, but it remains invisible and undetectable by conventional telescopes. Its elusive nature makes it one of the most intriguing mysteries in modern astronomy. Understanding dark matter is key to unlocking the secrets of universe evolution and the overall structure of the universe. The possibility of other universes, or a multiverse, is another topic that continues to spark debate among scientists. While the idea of a multiverse remains speculative, it presents the tantalizing possibility that there are countless other universes beyond our own, each with its own set of physical laws and properties. This idea arises from certain interpretations of quantum mechanics and the theory of infinite expansion. If these ideas are correct, our universe may be just one of many existing alongside others in a vast interconnected multiverse. However, proving the existence of other universes is an extraordinarily difficult task, as they would exist beyond our observable universe, and there would be no way to gather direct evidence of their existence. As we continue to push the limits of human knowledge and technological capabilities, it's clear that our understanding of the universe will continue to evolve. The discoveries made by the James Webb Space Telescope and other space-based observatories will no doubt lead to new insights and potentially challenge our current understanding of cosmology. However, even so, many questions will remain unanswered, and some parts of the universe will always remain a mystery. As we look ahead, the quest for answers will continue, fueled by our unwavering curiosity and the desire to explore the unknown. In the coming decades, it is possible that new breakthroughs in technology, such as advanced telescopes or even interstellar probes, could provide us with even deeper insights into the universe. The dream of reaching distant stars, exploring exoplanets, and understanding the true nature of dark matter and dark energy may one day become a reality. Until then, we must continue to rely on the tools and data we have at our disposal, including the groundbreaking work being done by the James Webb Space Telescope. Ultimately, the exploration of the universe is not just about uncovering new facts or solving scientific mysteries. It is also about expanding our perspective and understanding our place in the universe. The immensity of the universe is a humbling reminder of the fragility and transient nature of human life. As we continue to gaze outward and explore the farthest reaches of space, we are reminded that the universe is far bigger and more complex than we can fully comprehend, and our journey to understand it is just beginning.